Yes, sir.
Okay. So I'll just revise the statement of okay. So I'll just start. So we had seen the statement of Fermat's theorem yesterday, Fermat's little theorem. I'll just write the statement here again for your reference. So if okay, okay. So and we had said some examples of Fermat's little theorem. Now what I would uh, like what I will do now is just summarize those steps in a different way. Okay. So we had to calculate a raised to b mod. We had to calculate a raised to b mod p. Okay. So essentially we tried to factor a raised to b. We tried to factor a raised to b as uh, a raised to p minus 1 into a raised to p minus 1. Okay. All the factors of a raised to p minus 1, and in the end something remained which we can call as a raised to c. Okay. So this c is nothing but b mod p minus 1. Okay. So we want to calculate a raised to b mod p, but we actually find out a raised to c. Okay, c is nothing but the remainder which is left after we divide b by p minus 1, and ultimately we end up calculating a raised to c mod p. Okay, so to illustrate what I'm saying, let's say we want to calculate 2 raised to 1000. We want to calculate the remainder. I'll say it in plain English in two ways. So one way is, if 2 raised to 1000 is divided by 13, what is the remainder? And other is, what is the value of 2 raised to 1000 modulo 13? Okay. So we want to calculate the remainder when 2 raised to 1000 is divided by 13. Okay. So now our B is nothing but 1000. So our C is 1000 mod 13. If you divide 1000 by 13, you'll get 83 as the quotient, and remainder is
So 1000 mod 12, no?
Oh yeah, sorry. Yes, 1000 mod 12. So what is the quotient that you get? 83 is the quotient. Right? What is the remainder? Remainder is 4. Okay. So effectively, you are calculating 2 raised to 4 mod 13. Okay, which is nothing but 3, which is your answer. Or like the remainder is 3. Okay, the answer is 3. Did you get these steps? Do you understand this?
Hello,
Yes?
sir.
Yes.
Why did you take 12?
Well, because if you see the theorem, we have a raised to p minus 1. So we want to find how many factors of p minus 1 are there in the power. So p minus 1 in this case is 13 minus 1, that is 12.
Okay, okay.
Okay. So yeah, we yesterday also we did the same thing, but we did not find c. Okay, we directly found the factors and we directly uh, solved it. But this is a more systematic way, and let's see. So the next thing is, this was about Fermat's theorem. After that, we studied about the totient function. Okay, so what do you mean by totient function? This is called as Euler's totient function, also called as phi function because the symbol is phi. And what is the value of phi of n? Anyone can speak out. N minus 1 if it is prime, but I just want one of you to say the definition verbally, orally. You unmute and say. Okay, I'll ask someone then. Aman is here. Aman is here. Aniket is here.
Yes, sir, but I don't understand it.
Phi of n.
Uh,
Yesterday
I
we had discussed the definition.
uh, yes, sir, but I understand. I don't understand it.
Okay. Ratnesh. Ratnesh is here. Okay. Sai Kiran. It is turning up to be attendance call. Okay. So whom can I ask? Okay. Yes. Who is speaking?
Sir, may I?
Yes. Yes. Okay.
So it's the number of integers j such that j is in between 1 to n, such that GCD of j and n is 1.
Yes. Correct. Good. So that is what is given by the totient function or phi function of n. Okay. So based on this function, now we have a theorem which in fact generalizes the Fermat's theorem. Okay. So the theorem says if a and n are relatively prime, if a and n are relatively prime, that is the GCD is 1, or that is they do not have any common divisors, okay, then a raised to phi of n is congruent to 1 mod n. Now note the fact that n is not a prime. So if you compare it with the Fermat's theorem, in Fermat's theorem you had a prime number over here. Okay. So instead of that prime number, now you have any number, integer that is. Okay. Any integer you have here. N can be any integer. And for that, now here instead of p minus 1, we have phi of n. Okay. Because see, and you can also go back to the Fermat's theorem from this one. Okay. So do you see this point? How this can be reduced to the Fermat's theorem? Can anyone explain? How can you reduce this theorem to Fermat's theorem? This is called as Euler's theorem or Euler's theorem. Okay, Euler's theorem. Who can answer? Pratik?
Yes, sir. Sir, here n minus means n is not prime, right?
N can be prime or cannot, may or may not be prime
Yeah, may or may not be prime.
in Euler's
But
theorem. Yes,
but
but
in
if,
Fermat's, it's always prime.
so can you can you go to Fermat's theorem from this theorem? Does Fermat's theorem follow from the Euler's theorem? That is what I'm asking. Can you see the similarity?
Yes, when n is prime, there will be n minus 1 quotient function.
Yeah, correct. Okay, right. By the way, this is totient function. Okay, totient, not quotient. Totient function. T. It is called as totient function or phi function. Phi function or totient function. Okay. So if n is prime, then totient function of n, totient function of any prime number is n minus 1. Okay. So if we have a p over here, then it will be a raised to p congruent to 1 mod p, which is nothing but the Fermat's theorem. Okay. But if it is not a prime, then we cannot apply Fermat's theorem. Then we will apply Euler's theorem. Euler's theorem requires that, and also the condition of the Fermat's theorem was P should not divide A, right? In this case, the condition is A and N should not have any common factor. That is, they should be relatively prime. Okay, so we can say that Euler's theorem is a generalization of the Fermat's theorem. Okay, again, now we'll try to solve some examples using Euler's theorem. Again, we'll follow the same steps. I'll write the steps again. So if you want to compute a raised to b mod n, then first you will find phi of n. Okay, first step is to find phi of n. Then you have to calculate c as b mod phi of n, and then a raised to b mod n gets simplified into calculating a raised to c mod n. Okay, almost similar steps to this one. Instead of p minus 1, we have phi of n. Okay. Same steps. So let's say the question is find the last digit of 7 raised to 2021. Okay, so finding the last digit is like finding the mod with modulus as 10. Okay, so we are calculating 7 raised to 2021 mod 10. So phi of n, yesterday we had calculated phi of 10. Phi of 10 is 4. Okay. So C is nothing but B mod phi of n. And because 2020 is divisible by 4, C is 1. Okay, so effectively we are calculating 7 raised to C mod 10. That is 7 raised to 1 mod 10, which is nothing but 7. So the last digit of 7 raised to 2021 is 7. Any questions, any doubts in this calculation? No? Okay. So let's say we want to find the last two digits of 7 raised to 2021. Okay. So effectively we are finding 7 raised to 2021 mod 100. What is phi of 100? We had calculated yesterday. Answer in the chat. What is phi of 100? 40. Yes, 40 is correct. So phi of 100 is 40. And we are calculating C. So C is 2021. No. Yes, the remainder is 21. So 2021 mod 40. Okay, which is 21. Remainder is 21. So the question gets simplified to 7 raised to 21 mod 100. Now the simplest way to solve this is, first of all, can you do it, or can you suggest in the chat how can we solve this? We have studied a lot of things right now. Like till this point, we have studied a lot of things in modular arithmetic. So what will we use for this? Bharat is here.
Yes, sir.
How can we calculate this? 7 raised to 21 mod 100. Okay, Aditya says by Fermat's theorem. Yes, answer. Okay. So Fermat's theorem cannot be directly used here. Okay. Directly it cannot be used. It can be used in combination with Chinese remainder theorem. Okay, so one of the ways to solve this is using Chinese remainder theorem. But even simpler way is, it looks like a brute force method, but no, we had seen this before. So 7 mod 100 is 7. Then 7 square mod 100. Okay, 49. 7 mod 100. This is trivial, so I'm not writing. 112 is mod 100. Then 7 raised to 4 mod 100. Now you will have to actually calculate up to this point. So 49 square you will have to calculate. What is 49 square? What is 49 square? 2401 is correct. So 2401 mod 100, and which gives us that the value is 1 mod 100. Okay, it is, use the congruence symbol. It is congruent to 1 mod 100. Now our life becomes simple. Okay, so effectively what we are doing is we are simplifying 7 raised to 21 mod 100 as, okay, as 7 raised to 4, you know, into 7 raised to 4 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 5 times into 7 mod 100. Okay, one other way could have been that you could calculate 7 raised to 8 and 7 raised to 16. I'll also do that. Okay, but if you go this way, then you can get that you can separate all of these. So it is congruent to 7 raised to 4 mod 100 into 7 raised to 4 mod 100 into 7 raised to 4 mod 100. Okay, all of these are congruent to 1 mod 100, and what remains is just 7. Okay, so 7 mod 100. So the last two digits are, do you get this calculation? Yes, 07. Last two digits are 07. Any questions in this calculation? Anyone has? Okay, so instead of this kind of a split, we could have continued with this series basically, and we are squaring. Okay, so from 7 we found 7 square, 7 square, 7 raised to 4. Now 7 raised to 4 is simplified to just 1 mod 100. So we could have squared 7 raised to 4, which gives us 7 raised to 8 mod 100, which is congruent to 1 mod 100. Then again square this. So 7 raised to 16 mod 100 is congruent to 1 mod 100. And then we could say that 7 raised to 21 is equal to 7 raised to 16 plus 4 plus 1. Okay, that is 7 raised to 16 into 7 raised to 4 into 7 mod 100. So this is 1 congruent to 1 mod 100. This is congruent to 1 mod 100, and this remains. Okay, Arun, what is your doubt? Can you specifically ask, unmute and ask? Raman, what is your question? Yes.
No, sir, you're asking any doubt. That's why it's no, sir.
No, sir. Like no doubts.
No doubts.
Okay, fine. So this is okay. So this was the Euler's theorem and its application. Okay. So all this that we are studying, these are all topics of elementary number theory. Okay. This is all number theory that we have studied till now. Modular arithmetic and all these theorems and whatever we have studied comes under elementary number theory. So you see your syllabus, there is also some part of abstract algebra in your first module. Okay, so we'll go to abstract algebra and we'll study something uh, which is a combination of abstract algebra and number theory. Okay, so let's go for a while to abstract algebra and we'll return to number theory after that. Okay, so abstract algebra. Okay, so I'll directly go into the definition. Okay, so the idea, okay, I'll just explain you. Yeah, I'll explain you with an example maybe first. Now we are all aware of what do you mean by modulo 4. Okay. So what happens is we can have a structure such that there is a set. Okay, you all know the common sets that are there. N is a set of natural numbers, R is a set of real numbers, Z is a set of integers, C is a set of complex numbers, Q is a set of irrational numbers, uh, rational numbers, and whenever you prefix it, not prefix, we can say whenever you add a superscript. So if I say n plus, it means positive natural numbers, n minus negative natural numbers, z plus positive integers, z minus negative integers. Okay, so we can create a structure such that that structure has a set. That structure has a set and some operation on it. Okay, so this is the set of integers defined along with the operation of addition. Okay, then we can have z minus any such operation. This is the structure. Okay, now let's go to definition of a group. Okay, and I'll give you an example which will make it easy to understand. Example based on modular arithmetic. Okay, so a group is defined as a set G along with binary operation dot. Dot is a binary operation. It is not. It can be addition, any operation. It can be. Okay, so G is a set. Okay, G is a set, and dot is a binary operation. Dot is a binary operation, and it satisfies the following properties. First property is closure. Closure means that now I will use this language of logic. Okay, so this is for all. Okay, it's like upside down A. Upside down A. Okay. So for all x and y, for all x and y belonging to G. Pay attention to how I'm saying it. For all x and y belonging to G, we have x dot y also belongs to G. For all x, y belonging to G, x dot y also belongs to G. That is, if you take any two elements of the set and you perform the operation, the result of that operation will also be in the set itself. That is called as closure. Okay. Second is associativity. Associativity means for all x, y, z belonging to G, x dot y dot z is the same as x dot y dot z. That is, for this triplet of numbers x, y, z, if you want to perform the operation, you can either perform it on xy first or you can perform it on yz first. It will not affect the result, basically. Then the third one is identity. Identity means, now we have seen for all, Another such, now these are called as quantifiers. Okay, this is side information, not a part of this subject. It is a part of logic symbols. So this is for all. This is there exists. There exists. These are called as quantifiers. So this is universal quantifier and this is existential quantifier. Not a part of this subject, but it makes it easier to read and write. So this existential quantifier. Okay, so identity means there exists some E. There exists some E belonging to G such that for all X belonging to G, I'll write it in set builder notation. Okay, so horizontal bar means such that. So there exists E belonging to G such that for all X belonging to G, E dot G is equal to G dot E is equal to G. Then we call E as the identity of the group, and the group should have an identity element. The group should have an identity element. And fourth one is inverse.
Excuse me, sir. Just a small question.
Yes,
In the third one, that E dot G, is it capital G or small g?
small g.
And is it different from the earlier G, which you have mentioned over here? Like there for all E belongs to G.
Okay, I got it, I got it. Here I should not have used g. Okay, makes it confusing because I have used x over here.
Yes.
I mean to say, so thank you for pointing that out. So here I should use x. For all x belonging to G, we have E dot x is equal to x dot E, which is equal to x. Okay, basically what I meant was that small g is an element
Yes.
of
Yes. Yes.
capital
Yes.
G.
Yes.
Okay,
Okay.
but I had used x here, so x is better. X
Okay.
is an
It's
element.
fine.
So
It's clear.
inverse. Inverse means for all x belonging to G, there exists y belonging to G, again in set builder form, such that x dot y is equal to y dot x is equal to E. Okay. Now here the issue is, as you have studied in matrices, inverse and identity. Okay, if for example matrices you have freshly studied. Okay, so you have those in mind. So if you study any matrix, most of the properties it will not follow from this table. If you see, like for matrix, left identity matrix, if matrix is not a square matrix, then left identity is not the same as right identity. Dimensions itself are different. Similarly, in case of inverse, left inverse and right inverse will be different basically. So in inverse, there can be a left inverse and right inverse. But if it is to be proved as a group, then left inverse should be equal to right inverse. Okay, this is the right inverse actually because we're multiplying on the right, or operating on the right. Operating is the right word. We are operating on the right. So for all elements x belonging to G, there exists an inverse y such that x when operated by y on the left is the same as x when operated by y, the, the same y on the right. So the left inverse is same as the right inverse, and which is equal to E. So if G and dot, if the set G and the operation dot follow all these four properties, then we call it as a group. Okay, now let's take an example of, for example, now we'll call this as Z4. Z4 is equal to 0, 1, 2, 3. Okay, Z4 is 0, 1, 2, 3. And the operation is, let's say, plus 4. Plus 4 means addition modulo 4, which means that now, because this is Z4, so 2 plus 4, 3 will be equal to 5 mod 4, which is equal to 1. This is what is meant by plus 4. Okay, so we build a table, and this table is also called as Cayley's table. This table is called as Cayley's table. So we build this table, and we'll find out the result first, because we have to check the closure. Okay, so we'll see what result is obtained when every element is operated with every other element. Okay, so in case of 0, it is directly 0, 1, 2, 3. In case of 1, it is 1, 2, 1 plus 2 is 3, and 1 plus 3 is 4, but 4 mod 4 is 0. Then 2 plus 0 is 0, 2 plus 1 is 3, 2 plus 2 is 4, 4 mod 4 is 0, 2 plus 3 is 5, 5 mod 4 is 1, 3 plus 0 is 3, 3 plus 1 is 4, 4 mod 4 is 0, 3 plus 2 is 5, 5 mod 4 is 1, 3 plus 3 is 6, 6 mod 4 is 2. Okay, so this is the Cayley's table that we have. So from this table, we can say that the group is, the first property is, okay, we'll check the properties. The first property is closure. So as you can see, all the results are within the set Z4, that is 0, 1, 2, 3. Okay. Then the second is associativity. So whichever we add first, okay, because it is addition, so we know that addition is associative. Now identity. As you can see, the row and column of 0 is the same as the headers, either row wise or column wise. Okay, so 0 is the 0 is the identity. And what about the inverse? So inverse, for each element you will have to find it separately. So you can form a table like this. So when x is 0, what do you mean by inverse? You see, it should give you the identity. So 0 plus 0 gives you the identity. In case of 1, 1 plus 3 gives you the identity. In case of 2, 2 itself gives you the identity. And in case of 3, inverse is 1. Because 3 plus 1 is 4, and 4 mod 4 is 0. Okay. These are the inverses. So it follows all the 4 properties of a group. Therefore, it is a group. Is everything clear, or any doubts? Any questions in this?
Sir, repeat this E part.
E is the identity element. So this element should be such that, why is E 0? Because if you see the row of 0, anything which is operated with the identity remains the same. So 0 operated with 0 remains same, 1 operated with 0 remains same, 2 operated with 0 remains the same, and 3 operated with 0 remains the same. So you can check either the row or the column. Okay, in both cases, even if you check for the column that like 0
Operated means addition,
operated
sir.
means yes, addition modulo 4. In this case, addition modulo 4.
Okay.
But in general, we say operated. Okay, so okay, is it clear then? Alright.
Sir, the table.
This
This
table,
one.
yeah.
Yeah. Yes. Sir.
Okay, so we are finding inverses. So as we had used the alphabet Y for the inverse in this definition, okay, for the inverse. So I'm using Y here. So X are the elements and Y are their inverses. So element is 0. The inverse should be such that element plus its inverse should give the identity mod 4. That is okay. So X plus 4Y should be equal to E, and E in this case is 0. Okay, so 0 plus 0 mod 4 is 0. 1 plus 3 mod 4 is 0. 2 plus 2 mod 4 is 0. And 3 plus 1 mod 4 is 0. Okay, did you get
Yes,
it?
sir.
Okay,
Yes.
so that is a group.
So
Then
we can also make a table for E equal to 1, like E make for E equal to 0.
E will be 1 in case of multiplication, right? If you use E equal to 1 over here, it will not be an identity.
Yes.
Okay. So in addition to these 4 properties, that is closure, associativity, identity, and inverse. Okay. Okay. A group that is G and dot, which is commutative. Now, commutative means for all x and y belonging to G, x dot y is the same as y dot x. A group which is commutative is called an abelian group, named after the mathematician Abel. So, abelian group. Okay, so the above group is also abelian because it is addition after all. So x plus 4y is the same as y plus 4x. Okay, then is it clear? This is just a definition, just a terminology. Okay, abelian group. Okay, so this is all about a group. Now a ring a ring is a ring is a set R along with, now for a group we had only one operation. Now for a ring we have two operations along with two operations. So if we have set and one operation, it is a group, and it can be a group. Okay, and if it follows those 4 properties, and a set with 2 operations. Okay, now I'm using this. You can use any symbol, but I'm using this symbol. This is not literally addition, just a symbol that I'm using, not literally addition. Okay, so with 2 operations plus and dot, we satisfy the following. So first condition for a ring is that R plus must be an abelian group. R plus must be an abelian group. R so this dot operation that we have is associative with respect to R. It is the result should be within R itself. It's like saying closure and associated it together. So it is associative. Then there is an identity element with respect to dot. There exists, I'll write it in mathematical notation. So for all x belonging to R, for all x belonging to R, the identity is unique. So E dot x is equal to x dot E, which is equal to x itself. Okay, for all x belonging to R, there is an E within R such that it is same for all the x. That is my point. Okay. Then the fourth one is, we can call these as the distributive laws. Distributive laws. So dot distributes over plus. Okay, x dot y plus z is equal to x dot y plus x dot z.